All right, good morning, everybody. Today we're going to look at a couple of new topics. We've kind of mentioned them before already, but it's time to spend a little bit more time looking at them. So we're going to talk about current and voltage today. But first, before we do that, we looked at a couple of different types of circuits in the last lesson, but we're going to now look at two different ways of categorizing circuits, all right? Now, think about what we've looked at so far. So every circuit example that we've looked at, if you flip the switch, everything turns on. You flip it again, everything turns off. But if you think about it, when you turn on lights in, say, your bedroom in the house, does everything in your house turn on? If a light bulb burns out in your bedroom, does the power in your house entirely turn off? No, of course not. So obviously there's more than one way to set up a circuit. So the first one we'll look at is what we've already looked at. Right? So what we've looked at so far is what's called a series circuit. And if you look at the diagram, over here you can see we have a single cell, we've got a battery, there's a negative end, the positive end. So the electrons come out, they go through the wire, they pass through light bulb number 1, they pass through light bulb number 2, and they go back. There's only one pathway for it. Right? And then there's a schematic drawing for it too. So there's a symbol for the battery, symbol for the light bulb, symbol for the light bulb. So the electrons come out, they go through the bulbs, and they go back. There's only one possible way for the electrons to get from the negative to the positive. There's no other way for them to go. Right? Now, the other possibility is what's called a parallel circuit. So in a parallel circuit, there's more than one way for an electron to get from the negative to the positive. So if you look at this example, the electrons will come out of here, and then they hit this point D, and then there's actually two possible ways for them to go. Now, it's not like an electron has a brain. They're not going to actually think, okay, I want to go this way, or I want to go this way. It's just going to work kind of like if you were to pour water down a chute, and then you put a rock in the middle of it, right? So, or think of even like a river, right? So like a river's flowing along and there's a little island in the middle. The water particles don't actually consciously think, I want to go left or right of the island. They just kind of flow in that direction, okay? So the same thing is going to happen here. Now, depending on what you have in each of those pathways, the amount of electrons might change. So more might go this way or more might go this way. But that's something for the future. Right? We're not going to look at where or how that is decided. Okay. For now, all we're going to say is, at this point, electrons can either go this way, or they can go this way. Now, what you might think is it gets back to here, and then the electrons can, oh, well, if the electron's coming from here, could it go this way or this way? Well, no, because remember, electrons are always going from the negative to the positive. If the electron was to go this way, it would be going away from the positive, right? So it's never going to happen. It's always going to go this way, right? So where those two wires, this one and this one, join up here, all the electrons will then flow back to the positive, okay? So again, series circuit, one possible pathway. In a parallel circuit, we have more than one, right? So here's one pathway, and here's another possible pathway. Right? So that way, if this light bulb burns out, for example, this light bulb will still stay on. If this light bulb burned out, everything turns off, because there's no way for the electrons to get from this side to this side. So in this scenario, one light bulb burns out, they both turn off. In this scenario, one light bulb burns out, this one will still stay on. Okay, so there are situations where this might be better. There are situations where this might be better. Kind of depends on what you want to do with your circuit. All right. Okay, so let's get into current and voltage. So at the beginning of the introduction to electricity, we said, well, there are two things that are going to affect what an energy source like a battery is able to power. So if I take a single battery, what can I make run with it? There are two things that are going to affect it. Number one is what's called the current. So how many electrons can it produce every second? So how many electrons can come out of that battery every second? And the second is how strong are those electrons? So what is the voltage? All right. So the first one is the electric current. And the electric current we can define as the flow rate of electrons passing through a wire. Now, what we're doing is we are actually counting the number of electrons, right? So it's counting how much charge or how many electrons that pass through a wire every second. And the units for it are amperes. So just as kind of a comparison, think about if you wanted to measure how much you weigh. Right? You could measure it in pounds. You could measure it in kilograms. Those are two different units for it. Right? The units for electric current are in amperes. The symbol for that is A. The symbol for current is the capital letter I. Right? So if you're trying to figure out how much you weigh, and technically what you're trying to figure out is what your mass, the symbol for mass is M. But the units would be pounds, which are lb, or kilograms, which is kg. Right? So mass is measured in kilograms or pounds. Current, with the symbol of I, is measured in amperes. And the units you can shorten to A. Right? Now, we can actually measure what the current is in an electric circuit. And the tool we use to do that is what's called an ammeter. Right? So what that does is it basically acts as a counter. Right? So you can use an ammeter on a single point in a circuit. It's used in one spot. Now you can have more than one ammeter in a circuit, but an ammeter will only measure one point, and it's going to count the number of electrons that go by. Now it's connected in series, so it's actually part of the pathway. So we see here's a diagram here. So there's our battery. Here's our light bulb, and over here is the symbol A, and that symbol A is for ammeter. All right, so that means the ammeter is going to, right here at this spot in the circuit, count exactly how many electrons pass by every second. Okay, and so if we go check our handy little FET, I've got a little circuit set up here. We've got a battery, we've got a light bulb, and an ammeter is over here. All right, so you can see over here we've got voltmeters and ammeters. This is a pretty good way of actually just kind of getting an idea of what's going by. Right now, so you notice it's got this target here. If I put this anywhere on the circuit, it'll tell me how many electrons are going by per second. Now, this is kind of designed this way on this site just to kind of give you the idea that it's not actually part of the circuit. It's just a counter, right? So it just counts how many electrons are passing. So you can just use that. But if you want to know what it actually looks like when it's put in, it would be more like this, right? So if I cut here, I can take the ammeter and actually attach it in there. And so you can see the electrons come out of the battery, they go through the ammeter, so it's connected in series, and then go to the light bulb and then back. But you'll notice putting this in there didn't change anything about the circuit, right? The light bulb still stayed on, the flow of electrons was still the same. All this is doing is counting. That's it. All right? Now, the next is voltage. Now it's also referred to as potential difference. There are a lot of very similar sounding terms when we're talking about volts, voltage, potential difference, electric potential. There are a whole bunch of different ways of describing this. So it can sometimes be confusing because they're often used interchangeably. So try not to get confused by that. All right. So you'll typically hear it referred to as either voltage or potential difference, but there are other terms that you can hear. All right. So there are two ways to look at this. Number one is the loss of energy caused by electrical resistance when electrons flow through a conductor. What that means is when the electrons pass through either a wire or when they pass through a load, they are going to lose energy. Right? So that energy is going to be consumed by the load and then turned into something else. Right? It could be turned into light, it could be turned into heat, it could be turned into stored energy, for example, if you plug your phone into the wall. All right? Now, the other possible way to look at it is from the battery side. So we can say that the voltage is the gain in energy provided provided to electrons when passing through a power source. So the idea is kind of the same, right? It's the amount of energy that's changed. And that's why it's referred to as potential difference. Right? So it's how much change in energy. So how much change in energy is happening to those electrons when they either go through a battery and gain the energy, or when they go through a load and lose the energy. Right? The units for it are volts. This is kind of convenient. So voltage is measured in volts. Right? So it's easier to remember. So here's a kind of a way of visualizing what we're talking about here. So I've got a battery, I've got a fan, and I've got some wire. All right. Now the electrons are going to come up here through the fan. They're going to turn the fan, and then they'll come back. Now, when they come out of the battery, they have high voltage. Why? Because the battery gave those electrons stored energy. All right. They gave them electric potential or potential energy. Now, when it goes through the load, that energy is turned into making that fan turn. And so when they come back to the battery, they have low voltage. And in fact, when electrons come back to the battery, their voltage is 0. Right? Now, you can kind of think of it as like a water pump and pipes and a water wheel. Right? So this water pump is going to give this water, as it goes up, energy. And when it comes down through the water wheel, it can turn the wheel, right? Just like the electrons over here can turn the fan. So when the water molecules go passing through the water wheel turns, but then the water has low energy. There's low pressure here, right? So there's a big push from the water pump. So it has a lot of pressure behind it here, but then by the time it gets back to the water pump, the pressure is low. Okay? So, there are tools we can use to measure that. Voltmeter. So we use a voltmeter to measure the drop in electrical energy, or the pressure, between 2 points. Right? So, it's always going to be connected in parallel, which means, again, there's more than one pathway for the electrons. And if we look at a circuit diagram here, we've got our battery, we've got our light bulb, and this symbol V is for voltmeter. And you'll notice that the V has one wire here and one wire here. And the reason for that is a voltmeter will test or check the voltage of electrons here, and it'll check the voltage of electrons here, and it'll subtract the two. Right? So the difference between those 2 points is how much energy that light bulb used. So let's take a look over here. We have a handy little voltmeter over on the right. So if I take my voltmeter, and you see there's 2 wires, and I put one wire here at the side of the battery, and one wire here at the other side of the battery, you can see it says 9 volts. That's the voltage of the battery. And actually, if you click on the battery, you'll notice it gives you information about it, 9 volts. All right? If I do the same thing for the light bulb, it also says 9 volts. So over here, this tells me that the battery gives electrons 9 volts of energy as they go through, because the difference between here and here is 9 volts. So that means between when the electrons went in to when they came out, they gained 9 volts of energy. Over here, that light bulb is 9 volts. That means that between when the electrons go into the light bulb and when they come out, they lose 9 volts of energy. Right? So that is a 9 volt light bulb. Now, just as a test, well, what about the ammeter? Well, you see it's 0. Right? That tells us that the ammeter has no resistance. That means it's not taking energy away from the electrons. Right? And the same thing if we test, say, a section of wire. 0. That means that this section of wire isn't taking energy away from electrons. Now, in real life, there actually would be a difference. Right? So the wires will provide a little bit of resistance. And if you look over here, you can actually change how much resistance those wires have. But the amount is quite small. Right? It's not enough that we generally care about it. It only really has an effect when we start running wires over very long distances. Okay? All right, so I've mentioned the word resistance a few times. So let's talk about that quickly. So the resistance is a measure of a substance's ability to slow down the flow of electrons in an electric circuit. So, for example, conductors have an extremely low resistance. So our electrical wire has very little resistance, and as a result, the electrons don't get slowed down by it. Insulators, on the other hand, have a very high resistance. So, for example, if I were to, instead of having a wire, if I were to put a piece of eraser in there, the electrons would stop. Why? Because it has an extremely high resistance. It stops the electrons from going through. Electrical loads, like a light bulb, generally fall somewhere in between. Right? It depends on what the load is. Some have a very high resistance. Some have a very low resistance. It really depends on what that load is. Okay? Now, when that flow of electrons is slowed down by load, the energy is actually consumed by the load, and it's turned into something useful. So in the case of a light bulb, it's turned into light and heat. Now, in a very efficient light bulb, in a good light bulb, it will be mostly light and only a little bit of heat. So that's something like an LED light bulb. But in an inefficient light bulb, and this is probably more along the lines of what most of you have seen in like a lamp, for example, it gives off a lot of heat, but it also gives off light. Right? But that heat and light came from the energy in the electrons. So the battery, or if you have it plugged into the wall, the power plant, have given electrons energy. That energy flows through the wire, and when it reaches the load, that energy is consumed by the load. Okay? All right, so a couple of videos that I'd like you to watch, just kind of reviewing this, and then once you're done watching the videos, there is an assignment for you to work on. All right? You have until Monday to complete the assignment, so you've got lots of time. So if you have any questions, let me know.